Okay, I hope the sound is good. Um, my name is Kip Trout. I'll be the instructor for the semester, and I'm going to go through this, the first two lecture notes that are posted in PDF format in Canvas. I have combined those into this first video lecture because the first lecture is really a very quick introduction and pretty much a review of things that hopefully you know coming into the course. So the purpose of this is if you don't know some of these things, that you will get up to speed on them as quickly as possible. The calculus you need to know for the course will be pretty much taught as we go, but your algebra and trig skills need to be up to date and ready to go. Okay, so if this is your first physics course, it's important that you understand that physics is a science. Okay, it's one of the natural sciences, and science and technology are different. Okay, science has to do with the discovering of relationships in nature. All right, scientists aren't concerned with people's opinions of what they're doing. A scientist searches for physical facts and truths regardless of whether they are useful to the public or not. So scientists are really trying to figure out the blueprints for how the universe works. In other words, what are the rules that the universe is following? Technology, on the other hand, deals with the tools, techniques, and procedures for making practical use of the facts that science discovers. So computer websites, engineering type people, they're the technology people, and technology emphasizes people and is only concerned with what is practical and useful to people. Technology is very concerned with the reactions of the public. If the people will not like it, technology stays away from it. So scientists, again, are looking for the rules, whether the rules at the present time seem useful or not. Technology people were generally more interested in practical application of the rules. And so, for example, somebody could create a toilet that flushes with all kind of pretty water patterns and, has watercolors in there and pretty swirly things and everything else and plays music and so on and so forth. But, typically, for the amount of money that that's going to cost, the average person is not going to buy that. So that's the type of thing that technology tends to veer away from. On the other hand, a little device that you can hold in your hand and communicate with people audibly or with texting and show videos and collect images and so on and so forth, like your smartphones, that's a very useful thing that the public would be interested in, and so technology embraces and pursues things like that. So that's the main difference between the two. So what is physics as a science? What makes physics different than some of the other sciences? Well, physics is the basic science, okay? Physics addresses the most fundamental basic things such as matter, motion, forces, energy, etc. Physics is trying to answer questions like, what is the smallest building block of matter? What's the smallest thing that things are made out of? How is the universe formed, and when was it formed? How old is the universe? These are types of questions that physics is interested in. Physics always tries to come up with the simplest, most universal relationships. Ultimately, we'd love one equation that describes every different possible physical interaction in the universe. Okay, so physics as the basic science is the foundation for all the other sciences because it's the oldest and most basic of them all. If you go back to the beginning of in history to the development of modern Western Hemisphere physics or science, it starts with physics. Actually, physics and astronomy and mathematics were all kind of intertwined at the beginning. Even religion was intertwined in there. But pretty much as modern science developed, these different branches of science came out of that. So as you notice, this science tree shown at the right, it has different areas of science. So some of you might be interested in biology, geology, chemistry, so on and so forth. And these all kind of grew branched out from this original science of physics, astronomy, and math, whatever you want to call it. Typically we say it's physics because it was Galileo and Isaac Newton that formed the foundation of this tree, basically. So a good understanding of any science starts with a good understanding of physics. And so hopefully this image of the science tree helps you kind of visualize better how, why this physics is important and how science developed. Now we can work toward becoming a good scientist or even engineer, because they are related fields, by developing some good habits. For example, observation, curiosity, logic, knowledge, time and effort, and attitude. These are all important factors. Here you see in this little cartoon, one-page comic, the detective says, we've got the murder weapon and the motive. Now if we can just establish the time of death. So what is the good habit this guy is missing? What is the good habit this guy is missing? Well, I would probably argue it's observation. I mean, there's a bunch of clocks that were shot up there at the time of the crime, apparently, and they're all stopped there shortly after 10 o'clock. Some people might say he's not curious enough. He's not really curious to search the scene too well. Maybe his any of these, I guess, could be a reason he's not picking up on this. Maybe his logic's not good. He probably has the knowledge to know how to read a clock, so maybe his attitude, maybe he's in too big of a hurry. But anyway, you can see how it's just a funny little comic that demonstrates again that you can have things right before you, but if you don't have some good skills with observation, curiosity, logic, knowledge, time, effort, and attitude, you're not going to be very successful at this. So I encourage you, especially since this is a science course, to try to stay curious and interested in why things are the way they are. I think that's a very good thing. Now, knowledge is the next thing we want to talk some about, and those are the different things you want to know coming into the course. And so if you are lacking in any of that introductory knowledge, it's going to be on you to, outside of class, get that knowledge in place. Now, the good thing about logic is it can be improved with practice. And so I do have some logic exercises in here that you can work through outside of class time here and challenge yourself and work on your logic. Logic is a process of thinking that tends to be somewhat organized, and you can improve it with practice. Most of everything in life you can improve with practice. That's the good news. So let's take a look at this logic exercise. Josie and Ken went on a double date with their close friends Jane and Bull. They decided to go to McDonald's for burgers, fries, and shakes, and each person ate at least one of the foods. Okay? From the information provided, determine where each person sat at the table, positions A, B, C, or D, and the type of food or foods each person ate. Okay, that's your goal here in this exercise, and you've got a list of 5 specific facts, pieces of information that you're given. And what you want to do is use your logic and your reasoning to determine who is sitting at each seat and what they ate. Okay, so you may want to pause the video at this time and work on that to see how you do on it. Okay, so hopefully after a few minutes of work on your part, you were able to reason through those clues and to arrive at the correct answer, which is shown on your screen. If this was a difficult process for you or something that is not comfortable, then definitely outside of class you're going to want to continue to work on your logic skills. Okay, to be a good scientist or engineer, you need to have good logic skills, and so I'd encourage you to continue working on some more of these. Now you can find logic exercises all over the place. There's even booklets in bookstores, puzzle books and things you can get. But I've included 9 more logic exercises in this PowerPoint for you to practice through, to continue to improve your thinking and your logic skills. And so I'd encourage you to work on those. The answers to those logic exercises are posted in Canvas, and so you should be able to find a document in Canvas. I believe I put it in the homework module or homework answer module in Canvas for our course, and so it would be good for you to work through these in this PowerPoint. I'm going to kind of skip over them next, and you work on them outside of class, and you can check your work to see if you did them right with that document that's in Canvas. It's a good idea for you to get used to accessing Canvas pretty regularly. You want to be able to get in there to access your lecture notes, to get your homework solutions, even your quizzes will be posted in there. Okay, so it's important that you get very comfortable with accessing Canvas quite regularly. Your first web-assigned homework will be assigned soon here. In the meantime, get your WebAssign account set up, and then we will talk more about getting you up to speed on WebAssign. That's a separate website where you'll get your homework problems assigned to you, and you'll work through those and answer them. So that's all very important. It's going to take a lot of work outside of class for you, as we're going to talk about a little bit later in this lecture. You might be surprised at how much time is expected, but this is college after all, so the expectations are reasonable and realistic. Here's logic exercise 2. Again, we'll skip by that. You may note that sometimes it is helpful to make a chart when you're doing logic exercises. Logic exercise 3. And logic exercise 4, quite interesting and challenging. Logic exercise 5. Logic exercises 6 and 7. Logic exercise 8. Logic exercise 9. And finally, logic exercise number 10. So work through those and then check your answers with the answer page in Canvas. Certainly knowledge can be improved with practice as well. A lot of times it's just a matter of taking the time that is needed to memorize or to practice something enough that it becomes common knowledge in your head. One of the things that you should have seen already at some point, either in high school or already in college, is this idea of scientific notation. If you're not familiar with that, you'll want to study up on this type of numerical or mathematical notation. It's a way of writing very large numbers or very small numbers in a compact way, and there should be ways to enter large and small numbers on your calculator using scientific notation. So this is expected knowledge. If you don't know how to do this, you can see me outside of class. Otherwise, just refresh your memory on it, or we'll just assume that you know that. Basic plane geometry, for example, if you have two straight lines that cross, then these opposite angles are equal in size, and knowing that if you have parallel lines that a line cutting across them, again, these alternating interior angles here, 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 and here are all equal size. Those are basic geometrical knowledge that is expected that you know coming into the course. So if you don't know it, go back and brush up on this stuff. Similar triangles come up quite a bit in physics, especially in mechanics, which is what Physics 211 is focused on. And so understanding what similar triangles are, and the fact that the ratio of their sides is all the same and they have the same angles, even though they might be different sizes. Understanding similar triangles, well, that's important. Knowing your mensuration formulas for perimeters, area, surface area, volume, knowing how to calculate those things for a variety of different shapes right off the top of your head is an important knowledge that you'll want to have, or the ability to reason through them on the fly. So for example, if you didn't remember the surface area of a right circular cylinder, or the can shape there, hopefully you'll be able to reason through and say, well, let's see, the ends of the can are circles, so pi r squared, and then for one of the ends, and then there's two ends, so 2 times pi r squared would give us the area of the ends of the can, and then 2 pi r would be the circumference around the circle, times the height of the can would give us the area of the side of the can, and so adding those together would give us the surface area of that right circular cylinder, or that can shape. So hopefully you know many of these. If you don't know them, one great way to get to know them is to, on one side of an index card, just write, triangle. On the other side of the triangle, or the other side of the card, write the equation for the area of a triangle, 1/2 base times height. And carry these cards around with you, just little business, business card or note card size things with you. And then when you're sitting waiting for an appointment at a dentist office or something like that, you just pull them out and work on memorizing them. And once you have them memorized, that'll make your science and engineering classes that much easier. Of course, knowing all your rules for algebra, being good at your algebra, that is an incredibly important skill. that you want to have in coming into this course. So if your algebra skills are not good, you need to continue to work on those. Algebra problems, difficulties with doing algebra, those things do not go away by ignoring them. If there's a rule that you're forgetting, if there's something that you don't understand about how the algebra works, these couple of pages summarize this and can be helpful in reviewing, but you want to be up to speed and really solid on your algebra. Again, here are some more basic algebra rules in case you forget them. Now, as I mentioned, time and effort in this course is going to be a big factor. I think with putting the proper amount of time in and putting a strong effort in, I think many of you will be very successful. However, that's the biggest thing I think that can cause you to struggle in this course, is not putting in the time needed or a strong enough effort. Now, if you worked a full-time job, most people that work a full-time job work about 40, maybe 45 hours per week with a little bit of overtime. I think that's probably pretty typical. And so if you're a full-time student, that's pretty much what is being expected of you during a regular semester. If they call you a full-time student, that basically means you are doing that full-time. You don't really have time to work a job because you're a full-time student. At least that's what that means as far as the people loaning you money and so forth. And so that's kind of what most people may have to work at to be a full-time student. Now, the average load for a full-time student, at least here at Penn State, is about 15 credits per semester. So 45 hours per week divided by 15 credits is about 3 hours per credit per week during a regular semester. Okay, that's during a regular semester. However, keep in mind, we are going to be doing this course in 6 weeks, or about 2.5 times the pace. Penn State normally has a 15-week semester. So doing it in 6 weeks, we're looking at a pace of about 2.5 times the normal pace. And so what we're looking at here is about 7.5 hours per credit per week. Now, Physics 211 is a 4-credit course. 4-credit course. So when you do the math on this, yep, you're looking at a really big time commitment here over the next 6 weeks. Okay, about 30 hours per week. That's what, 3/4 of a full-time job just for this one course. So my recommendation is that you come into the course realizing this time commitment and understand that you're not going to have much time for anything else over the next 6 weeks. So I certainly do not recommend working a full-time job while trying to take this course over the next 6 weeks. It's up to you, obviously, but you're going to be pretty exhausted if you're meeting the time commitments. So the good news is, again, if you watch the recorded video lectures for the course and you put in the time for the Zoom sessions, you're going to be in class about 12 hours per week, okay, just doing that. And so we're looking at about 18 hours per week outside of class time. That means working on homework, reading the books, studying online problems, looking at help things online that you find that you can use to help yourself in the class, whatever, asking questions. It's a very big time commitment. So that's, you've got to come into the class realistically understanding that, especially for this accelerated 6-week summer session. The good news is if you put that time and energy in 6 weeks, you'll have this course behind you. It goes pretty fast, but you cannot fall behind, and you have to come into it with this understanding that this is going to be a very, very important commitment in your life for the next 6 weeks. An often overlooked important point here in terms of being successful in the course is attitude. Sometimes your attitude, depending on how you're doing in the course, let's say you struggle a little bit in the course, it can tend to start to sour your attitude. And if you have a bad attitude towards the class, typically you're not going to do well in that. This is a huge thing. I think people underestimate the power of this attitude. By developing a good attitude or resisting the temptations of having a bad attitude, you might have students around you in the class that have a bad attitude about it, but resisting that and continuing to keep a positive attitude yourself is hugely important in terms of your success. Remember, I was a student at one time as well, and this is one of the things I found that made a bigger difference than I ever imagined possible. So, just developing some kind of self-talk things that you kind of say to yourself in your mind that are reaffirming and positive and keep you going, I think is huge. So, things like I have on this page, I can do this. Wow, look what I just learned. Gee, I never knew that before. I just need to keep doing my best. And I do understand some of these homework problems. Try to emphasize the positive, try to be optimistic, try to keep your motivation strong. That'll pay dividends by the end of the course. Okay, so that's my brief introduction to the course, and in terms of what knowledge you should have coming in and some suggestions for how to be successful in the course. That takes us into chapter 1 now, which is measurement. Okay, and again, I'm not going to spend a lot of time on this chapter because many of you have probably, especially if you've had some other science courses, either in high school or college, some of these things may already be somewhat familiar to you. So I don't want to waste a lot of time on it. But on the other hand, again, this is a foundational chapter in terms of understanding the basics of the units that we're going to use, understanding the basics of what the expectations are for you being able to convert units and so forth. So I do want to take just a couple minutes to cover this. And first of all, physics is a numerical science. So, measurements are very important, and of course, units are incredibly important with that. If I ask two people to measure the length of a table, one person may say 4 and the other person may say 48. And you may say, well, do they agree or do they disagree? Well, we don't know until we check the units. For example, one person may have measured in feet, and so they may be reporting the answer as 4 feet, and the other person may be reporting the answer in inches, 48 inches. So they may very well agree in terms of their measurement, but they're using different units. And so units are incredibly important to keep track of and to pay attention to. The United States is about the only country in the world that's still clinging to the British system of units, and not even the British use the British system of units anymore, and that's the foot, pound, inch type of a system I was just discussing. So we are going to be using what's typically called the International System of Units, or the metric system, and one interesting place to start on that is that a unit that has historical significance but which is no longer used is using the unit of length to measure a pulse rate. It was typical to measure heartbeat rates per minute, or it is now typical to measure heartbeat rates in beats per minute. But in 1585, Galileo, who was a medical student at the time, discovered the principle of the pendulum while watching a chandelier swing in church, and he used his pulse to time the period of the swing. So in 1602, Sanctorius, a friend of Galileo's, measured pulses by adjusting the length of a pendulum until it swung in time to the patient's pulse rate. So in other words, your pulse rate would have been recorded as a length of the pendulum. For example, your pulse rate is 72 centimeters, or your pulse rate is 94 centimeters, something like that, which would be, by today's standards is a very odd sounding thing, but it goes to show you that units have changed through the years, and different units have been used for different things. But again, we have to have an agreeable set of units and understand what the units are in order to communicate in science. Again, here is a map showing the number of countries that are left in the world that don't formally use the International System of Units, and you can see what it is, like Burma, Liberia, and the United States of America. So as American students, unfortunately, you're going to have to be familiar with a couple of different sets of units. Certainly the International System of Units is not going to go away. You can see the number of countries there in green. It's pretty much the entire world that uses the International System. So we have to be familiar with that set of units. And even in modern day America, that's kind of the units that scientists tend to use. However, because we are an industrialized nation and very powerful industrialized nation, many of the engineering equipment and early on measurements as we developed machines were scaled to cut to a level of a thousandth of an inch or within a hundredth of an inch and things like that. And so we had so much machinery and so many people familiar with the old English system of units that as a free country, people can resist somewhat changing set of units. So our country's kind of resisted the change over to just changing to the international system of units. So we're kind of mixed up. We buy gallons of milk, gallons of gasoline, but yet we buy 2-liter bottles of soda. We talk about how many pounds we weigh, but then we talk about how many grams of fat are in our food, and so on and so forth. So we're kind of goofed up that way, and it's just the way it is, and you have to, just deal with it and be comfortable converting units and being familiar with different sets of units. And so pay attention to that when you're doing problems, because it's an incredibly important issue. The standard units that we will use as the base quantities for our units, lengths will be measured in meters. We abbreviate that with an M. Time will be measured in seconds as a standard unit, and we abbreviate that with an S, or sometimes an SEC for seconds. And then our masses will be measured in kilograms, which we abbreviate kg. So notice that the gram is not the base unit in the international system. It's the kilogram, which is 1,000 grams. And of course, you can't just keep somewhere, somebody has to have some kind of a standard, so that as years go by, we don't have our measurement of a meter drifting or our measurement of a kilogram drifting, and so on and so forth. So the standards for the base units of seconds, meters, and kilograms are defined. At one time they were actual physical devices, and they still are in some cases, I guess. I mean, these things are still there. But there's also definitions that have been made so that it's based on a natural quantity, and that makes it a little bit more stable in terms of keeping that unit the same as the years go on. So if you're interested, there's some definitions of what the exact definition of a kilogram is, and what the exact definition of a meter is, and exact definition of a second is. Again, the scales, can be so dramatic in terms of the smallest masses that we deal with and the largest masses we deal with. We've got many tens of magnitudes difference in things like a galaxy compared to an electron. So we're going to use the international system of units, but we're also going to remember we're going to be using the scientific notation quite a bit. Here you see some comparisons of scales throughout the universe. And here we see a comparison of periods of time from different scales throughout the universe. And of course, a convenient way to keep our scales easier to manage is not only with scientific notation, but also with these what we call metric prefixes. And so giga, G-I-G-A, is a prefix. If we put that in front of a meter, for example, a gigameter would be 10 to the 9th meters. And so if you know some of these prefixes, it can actually allow us to communicate at the appropriate scale level. So if I'm talking about something on a piece of paper, I might be using a unit of centimeters, where if I'm talking about distances between galaxies, I might be using terameters, or who knows, bigger than that even. So here are some of the most common prefixes: giga, mega, and kilo for making the values larger, and then centi, milli, micro, nano, and pico for making the unit smaller. So you should become familiar with these. Of course, if during a test or something somebody's talking about a zeta second or something like that, and you don't know what a zeta prefix means, of course you can ask, and I will help you out with that. But some of these ones that are in bold, those are ones you should probably get very familiar with, commit to memory, because they come up so often. So significant figures is something that a lot of students have forced upon them in high school science classes, and the teacher takes off points for not using the correct number of significant figures, and so on and so forth, and you get all paranoid about them, and you don't understand how they work exactly. Significant figures really only have application, or are most important in the lab setting, okay, when it comes time for data collection and so forth. So we are going to talk more about significant figures in the lab part of the course. Okay, one important thing, or a few important things to know about them at this point, though, is that your answers can never turn out to be more accurate than the numbers you put into your calculation. That is, your results can never be more accurate than your least accurate piece of data. So your calculator may give you 10 or 15 digits of display, but not all those digits are accurate. Okay. So the simplest way to determine, indicate, and keep track of significant figures is to write the number in scientific notation. So here's another important point about scientific notation. If you write the number in scientific notation, that will help you determine how many significant figures the measurement has. Okay, or you can indicate it in lab. You can indicate how many significant figures are in the measurement using scientific notation. So while performing an experiment, my recommendation is to use scientific notation if you have measurements that are, being recorded in a table or something like that. And so here's a quick example, comparing two different students, student A and student B. Student A here on the left writes down 400 micrometers. Okay, how many significant figures does that measurement have? So maybe it's in an experimental setting and they wrote down 400 micrometers. Well, you can't really tell how many significant figures that number has. It could have 1, 2, or 3. That number written down the way it is, if the person could measure to the nearest micrometer, then they're saying that the answer was between 390, or the measurement was between 399 micrometers and 401 micrometers. In that particular case, all 3 digits are significant, so it would have 3 significant figures. On the other hand, if they're using an instrument that's only accurate to the nearest 100 micrometers, in other words, if the answer was between, was 400, but it was between 300 and 500 micrometers on the scale, then maybe it's 400 micrometers plus or minus 100 micrometers, and in that case, the measurement only has 1 significant figure. So student B decided to write down the measurement using scientific notation. So they wrote their measurement as 4.0 times 10 to the minus 4 meters. In this case, it's very clear that there's 2 significant figures, okay, when it's written this way, because if we look at the left part, the left side here of the measurement written down in the scientific notation there, 4.0 it has 2 digits. And so both those digits are significant. The student is basically saying, hey, my answer was between 3.9 times 10 to the minus 4 meters and 4.1 times 10 to the minus 4 meters. So in other words, they're saying I'm using an instrument that's accurate to within 0.1 times 10 to the minus 4 meters, or what would be 10 micrometers. And so by writing it in scientific notation, it becomes very clear how many significant figures there were. Now, during homework, quizzes, tests, and so forth, I don't want you to be overly concerned with significant figures. My general rule here is, or advice is, to carry along plenty of extra digits. That is, don't round early on in your calculations, okay? It's better to carry along, it would actually be better to carry along all the digits on the calculator, or plenty extra, and then your final answer then can be rounded down to the right number of significant figures. But once you've rounded too early in the process, then you can't get those digits back. So if a student wrongly writes down too few digits early on in their calculation, and they get to the final answer, and they find, oh, geez, that had 4 digits of accuracy, and I only carried it out, 4 digits instead of carrying along a few extra digits. Now I have to redo my whole calculation. Whereas if you carry along all the digits, plenty of extra digits as you're doing your calculations, then when you get to the end, you can always, that answer is going to be correct, and then you can chop it down to the right number of significant figures. So it's better to err carrying too many digits than not enough. Okay, so let's look at this example. In 1792, the hour was actually redefined to provide a 10-hour day. The idea did not catch on, but the maker of this watch wisely provided a small dial that kept conventional 12-hour time. So the question that we're posed with here as an example, our first mathematical example in the course really, do the 2 dials indicate the same time? And so fortunately with this 10-hour watch in decimal form, we could say then, reading the large hands on this dial, that the time of day on the 10-hour clock is 8.23 hours out of a 10-hour day. okay, on the 10-hour clock. The 12-hour clock in conventional, the conventional clock shows that it's, what is that, about 16 minutes till 8, or about 7:44 on the clock, and we don't know whether that's AM or PM. But if these are going to read the same, considering that we are 8.23 hours through a 10-hour day, well, I guess, the 10 hours in a 24-hour day is our assumption here. So, because it says up here a 10-hour day. So we have to assume then that this is going to be PM if it's reading the correct time, right? Okay, so let's work out the math and see if these two dials read the same time. Okay, so let's see if we can work this out. We know when we start that we have 24 hours in a regular day is equal to 10 hours on this new clock. And I'm going to use a capital H here to stand for the new hour that's being defined on this clock. We also know that we have 60 minutes in one standard hour, with a small h, and there's 60 seconds in 1 minute. So we start with our information that this clock is reading 8.23 in the new hour time, 8.23, and we're going to multiply that by our conversion factor here, knowing that there's 24 standard hours in this new 10-hour day, and that will cancel our units of hours, and it will leave us with an answer in standard hours of 19.752 hours. All right, if you check on your calculator, should be 19.752. Now, we can subtract off of that 12 hours for our first time around the dial, we'll call it. Okay, first time around the dial on a standard clock. So that would be during the AM hours, right? And so what we're going to get here is a reading of, on a standard clock, of 7.752 hours in the PM, or in other words, 7 p.m., but we have this fraction of an hour left over of 0.752 standard hours. So if we take that 0.752 standard hours here, and we multiply that by 60 minutes in one standard hour, right? Another conversion factor here. We end up with 45.12 minutes. Oops, 45.12 minutes. And so that means putting that in place of our 0.752 hours here, our answer for this clock would be that it's 7:45 p.m. and then we have the 0.12 minutes, which would be down into the seconds. But if we just stop at the minute level, the clock should read, on a 24-hour clock, it should read 7:45 p.m. and that's close enough, I think, for typical everyday clock standards. So converting units is pretty much what Chapter 1's about. A lot of it is about units and keeping track of units and converting units. And so conversion factors are listed inside the back cover of your textbook in Appendix D. Here are some some typical conversions that we will use in this next exercise. 1 meter is 39.4 inches, 12 inches is 1 foot, 5,280 feet is a mile, and 1 pound is about 4.45 newtons. Okay, so at this point you may want to pause the video and work on these 3 unit conversions. Number 1, number 2, and number 3 here. The first one, how many newtons does a 160-pound man weigh? Number 2, how many meters are in 1 mile? And number 3, how many seconds are in 1 year? So what I'd like you to do is use those unit conversion factors that I just mentioned, and if you have to look them up in the back of your book or whatever in the appendix, that's fine as well. But pause the video and work on these 3 questions, and we'll see how you did. Okay, so let's see how you did. 160 pounds, if we multiply 4.45 newtons per pound, we get about 712 newtons. How many meters are in 1 mile? 1 mile is 5,280 feet. You'll notice that each time when we're doing these conversions, by the way, you'll notice that we're always multiplying by a fraction, and the fraction, each fraction is a 1. It's the same size unit over the same size, or it's a physical quantity over top of another physical quantity that are in different units but are the same size. So, for example, 4.45 newtons equals 1 pound, right? 4.45 newtons equals 1 pound. And so our fraction that we write, that's a 4, is going to be either 4.45 over 1 or 1 over 4.45, depending on which one will cancel the unit. And so here we have pounds up top to cancel with pounds on the bottom, so the newtons go up top. So we use our conversion factor of 4.45 newtons is 1 pound, and then we know that one's not the right one. So anyway, that's what we're doing here. In the second one, again, you'll note that 1 mile, we want to convert that into meters, and so we ultimately want to end up in meters while we're starting at miles. And so in between, we're multiplying by these fractions, which are basically the unit conversion factors, or the unit conversion equations, one over the other. So 5,280 feet is equal to 1 mile, so that will get us into feet. And then we know there's 12 inches in a foot, and so that'll cancel units of feet, and that'll get us into inches. And then from inches, we can get into meters, because we know, or that should say actually 1 meter here. That's a typographical error. So 1 meter is 39.4 inches. That'll cancel the units of inches. And so we end up with 1,608 meters. Okay, so make that correction in your notes here. This should not be feet right there. That should be meters. The third one, how many seconds are in a year? Once again, we start with years. We want to end up in seconds. And so we're going to be multiplying by these fractions, each fraction physically representing a 1, even though mathematically with units it's not 1. Okay, 1 year is 365 days, 365.25 days in a year. That gets rid of years. Then we have 24 hours in a day. That gets us into hours. And now we got to get rid of the units of hours, get it into minutes. So we do 60 minutes over an hour times 24 hours times 365.25. And that'll get us rid of our hours. We're into minutes. And then 60 seconds per minute. That will cancel the units of minutes, and we'll end up in the units of seconds. And if we do all that right, we get about 3.16 times 10 to the 7th seconds in a year. So hopefully that example of unit conversion helps you. When I was a student doing unit conversions, I was smart enough that I tended to just wing it and think about in my own mind what I needed to divide by or multiply by. And what I found is that sometimes I would make mistakes with that. So over the years, I've gotten more disciplined with that, and I encourage you to be that way by writing out your unit conversion factors as fractions, as I showed here in this example. Now, looking at the clock, with the time that you took to pause and work on some of those exercises, we are probably even past the 50-minute mark. So I think we'll stop here at this point for today's lecture, and I will pick up with motion in one dimension. We'll pick up with this slide for Friday's lecture.